Hi everybody, welcome back to Math 251. We are jumping straight back in to section 3.9. Today's mathematician of the day is Emmy Noether. She was a German Jewish mathematician who is known for her contributions to abstract algebra and theoretical physics. She died in 1935. She was an amazing mathematician. And did you know that the abacus was perhaps first invented around 2700 BC in Mesopotamia? They had a base 60 number system, which means that instead of counting to 10 and then starting over at 11, they counted to 60 and then they started over again, basically. So it's pretty remarkable that they invented this strange abacus with such a bizarre number system to us. So today we'll be talking about the derivatives of logarithmic and exponential functions. So far, we know that the derivative of e to the x is simply e to the x. We also know that the derivative of e to the kx is equal to k times e to the kx. We already know these two properties, and today we are going to learn some more. First, we are going to focus on the inverse properties for e to the x and natural log of x. I know for some of us it's been a while since we have seen the relationship between these two functions. So first of all, e raised to the power of natural log of x is equal to x for x greater than 0. And the natural log of e to the x is also equal to x. So this means that e to the power of x and natural log of x are inverse functions of each other, because if I compose them with each other, I get our variable x. Our next property says that y is equal to the natural log of x if and only if x is equal to e to the power of y. So this is another way how e to the power of x and natural log of x are related to each other. Remember, natural log of x is equal to log base e of x. It's just a special logarithm with base e. And finally, for real numbers, x and b greater than 0, we have this, it's going to look a little bit strange, but it will help us later on. So b to the power of x is the same thing as e to the power of natural log of b to the power of x, which is the same thing as e to the power of x natural log of b. Why are these true? Well, if I look at this first equality, the reason that this is true is because e to the natural log of x, this e and this natural log, basically, since they're inverses of each other, they cancel each other out. So I'm just left with this b to the power of x. That's why the first equality is true. And then going from here to here, the reason that this is true is because I can use logarithm properties to bring this x down in front of the logarithm. So that is why the second one is true. Again, this looks a little bit strange, and that's okay, but it will help us to solve some problems today. All right, next let's go over the derivative of natural log of x. This one is pretty straightforward. So the derivative of the natural log of x is equal to 1 over x for x greater than 0. We can't take the natural log of a negative number or 0. So x has to be greater than 0. And if we want to put an absolute value in there, the derivative of, my computer is doing all sorts of things. The derivative of the natural log of the absolute value of x here, my x can be anything now, since it's not restricted by having to be positive. This is equal to 1 over x for x not equal to 0. So if I throw an absolute value in there, then I can take this derivative for any x that is not 0. So this is only one very particular case, right? The natural log of x. So what about if I have a composite function? So if u, a function, is differentiable at x, and u of x is not equal to 0, then I have the following. The derivative of the natural log of u of x is equal to u prime of x over u of x. We would get this same result if I used the chain rule here. In fact, this is just a special version of the chain rule, but we can use this without having to use the chain rule directly. So if I take the natural log of a function, this is a composition of functions, the derivative of that is the derivative of the inside function over the inside function. So let's use this theorem here to find the derivatives of y is equal to natural log of 5x and y equals natural log of secant x. So if we look at this, that secant x has an absolute value around it, which just tells me when I can take the derivative of it according to this guy right here. But I wouldn't worry too much about the absolute value. So if I were to have the natural log of 5x, so here I'm taking the natural log of a function. So I'm going to call my u of x equal to 5x, right? Since I'm taking the natural log of a function. That means that u prime is equal to 5. And according to our theorem right here, this means that the derivative of natural log of 5x is equal to u prime, which is 5, over u of x, which is 5x. And I can cancel those 5's out. I'm left with a 1 over x. Okay, and then if I have y is equal to natural log secant x, well, here my u of x is equal to secant x. That means u prime is equal to secant x tangent x. So then the derivative of the natural log of secant x is equal to u prime, which is secant x tangent x, over u, that's secant x. And then I see here, since I have multiplication on the top, I can simply cancel out these secants, and I am left with tangent x. All right, so this is how we take the derivatives of composite functions with natural logs. So we know, in this next theorem, we already know that the derivative of e to the power of x is just equal to e to the power of x, right? But what about if I have a number other than e in my base here? Well, that is what this theorem is telling me. So if b is our base of this exponential function is greater than 0 and not equal to 1, then the derivative of b to the power of x is equal to the natural log of b times b to the power of x. And we can see how this is related to e to the power of x, right? So if I were to do a special case, right, so the derivative of e to the power of x, according to this rule, this is natural log of e times e to the power of x. Well, the natural log of e is equal to 1. So that is why this derivative is true for e to the x. But when I don't have e as a base, then the derivative of b to the power of x is the natural log of b times b to the x. All right. I would like for you to try this first example of example 2 on your own. So try to find the derivative of y is equal to 3 to the power of x, just the first one. Go ahead and give it a shot, and then we'll do it together. All right, so hopefully you've given that a try. So we have the function y equals 3 to the power of x. Well, here our base of our exponential is equal to 3. So that means that according to our theorem here, y prime is equal to natural log of 3 times 3 to the power of x. This next example, 108 times 2 to the power of t over 3, this is a little bit trickier. So let's do this one together. So I have g of t equals 108 times 2 to the power of t over 3. So in order to find this derivative, I see that g prime of t will be the derivative with respect to t of 108 times 2 to the power of t over 3. And I don't like that 108 hanging out in front of there. So I'm going to use the constant multiple rule and bring it out in front. So this is 108 times the derivative with respect to t of 2 to the power of t over 3. So here I have that I want to find the derivative of 2 to the power of t over 3. Well, according to my theorem that we just learned, I know how to take the derivative of 2 to the power of t, but what about that t over 3 hanging out in there? Well, this tells me that I'm going to have to use the chain rule. So my outer function f is equal to 2 to the power of t. My inner function g is equal to t over 3. That means that f prime is equal to natural log of 2 times 2 to the power of t, and g prime is equal to 1/3. So then, if I look at this g, I see that g prime of t is equal to 108. We can't forget about that constant. And then the derivative of 2 to the power of t over 3 is equal to f prime of g of t, according to our f's and g's here. So f prime of g of t would be natural log of 2 times 2 to the power of t over 3. That's f prime of g of t times g prime, which is 1/3. If I were to multiply this 108 with this 1/3, I could certainly do that, and we would just get 36 natural log of 2 times 2 to the power of t over 3. We could just combine our constants there. Okay, next we have sort of an application word problem. So we have a function p of a is equal to 1 over 1,613,000 times 1.2733 to the power of a. And this gives the percent of children born with Down syndrome, p, as a function of the mother's age in years, a. So I first want to determine at what age is the percent of children born with Down syndrome equal to 1%. So I want my p of a to be equal to 1. So let's break this into parts here. So I have, since I want the percent of children born with Down syndrome to be 1%, I have p of a is equal to 0.01. So if I set this function equal to 0.01, I get 0.01 is equal to 1 over 1,613,000 times 1.2733 to the power of a. If I were to multiply both sides by 1,613,000, so I multiply both sides by this constant, I would get, well, this guy would cancel, right? And if I multiply 0.01 by 1,613,000, I get 16,130 is equal to 1.2733 to the power of a. And I wanted to solve for a, right? That's what I'm after. So how do I solve for a in this situation? Well, one way to do that is to take the natural log of both sides, right? Here my a is in my exponent, so let's see what happens if I take the natural log of both sides. So I would get the natural log of 16,130 is equal to the natural log of 1.2733 to the power of a. But then according to my natural log rules, I can bring this a in the exponent down in front of the natural log. So I have the natural log of 16,130 is equal to a times the natural log of 1.2733. And now to solve for a, I simply am going to divide both sides by natural log of 1.2733. And this gives me a equals the natural log of 16,130 over the natural log of 1.2733. And if you type this into the calculator, this is approximately 40, and our units here is years. So what this means is if a mother is 40 years, then she has a 1% chance of giving birth to a child with Down syndrome. So the trick here was to take the natural log of both sides, since I wanted that a to come down in front of our expression. And then once I did that, I simply had to divide through by that natural log expression. All right, part B says to compute p prime of a. So I want to take the derivative of my function here. So p prime of a here, if I look at this, I'm going to bring this constant, 1 over 1,613,000, I'm going to bring it out in front. So p prime of a is equal to 1 over 1,613,000 times the derivative with respect to a of 1.2733 to the power of a. I'm just using the constant multiple rule here. And then according to my rule here, since I have the derivative of something raised to our variable, the derivative of this expression is equal to the natural log of 1.2733 times 1.2733 to the power of a. And if I were to simplify, so this is a constant, right? And this is a constant. And if I were to combine our two constants, this would be 1 over 6,676,000 times 1.2733 to the power of a. So this is the derivative of my function. And finally, we want to find p prime of 35 and interpret it in terms of this problem. So p prime of 35, well, I'll plug in 35 for this a here, since this expression is p prime. So this will be 1 over 6,676,000 times 1.2733 to the power of 35. If I put this into my calculator, this is approximately 0.0007. And what does this mean in terms of this problem? Well, we're finding p prime, and remember, derivatives are rates of change. So this means that when a mother is 35 years old, the incidence of children born with Down syndrome is changing or increasing since this number is positive, by a rate at 0.0007 per year. So the incidence of babies born with Down syndrome increases at a rate of 0.0007 per year at age 35. That is what P prime means in this context. So that's a good example of kind of this applications of these kinds of mathematical expressions. All right, we have another example here. Let f of x equal x to the power of cosine x. We want to find f prime and f prime of pi over 2. All right, so we are going to use one of our rules here. So if we go back up to, let's see, this expression right here, I'm going to use this guy. So I have f prime, excuse me, I want to find, so f of x is equal to x to the power of cosine x. And if I use that rule in terms of e and the natural log of b to the power of x, I'm going to rewrite this as e to the power of cosine x times the natural log of x. And you'll see why I do this here in a second. So if I were to have, so here I have a composition of a function, right? So I have e to the power of cosine x times natural log of x. This is the chain rule, right? In order to find the derivative of this, I'm going to have to use the chain rule. So my outer function is equal to e to the power of x. My inner function is equal to cosine x times natural log of x. This makes f prime of x equal to e to the power of x. And then here, I'm going to have to use the product rule. Okay, well here I'll set h, oops, I forgot that x, didn't I? H equal to cosine x and j equal to natural log of x in order to use the product rule here. That gives me h prime equals negative sine x and j prime equals 1 over x. So then g prime here is equal to the first times the derivative of the second plus the second times the derivative of the first. So now I have f, f prime, g, and g prime. I can plug this all into the chain rule now. So I see that f prime of g of x times g prime of x is equal to, well, f prime of x is equal to e to the power of g of x will be cosine x times natural log of x times g prime, which is cosine x times 1 over x plus, actually we'll do that minus sign, minus natural log of x times sine of x. Okay, but I want us to pay attention to this guy right here. e to the power of cosine x times natural log of x. Where else did we see that? Well, it's this guy right here. And I know that this is equal to x to the power of cosine x. So I can rewrite this as x to the power of cosine x times cosine x over x plus, minus natural log of x times sine x. So this is our derivative here. Since I know that e to the power of cosine x times natural log of x is equal to x to the power of cosine x, I can replace it in our expression. If I wanted to find f prime of pi over 2, I would plug in pi over 2 here. So let's see, f prime of pi over 2 is equal to pi over 2 to the power of, well, what is the cosine of pi over 2? It's equal to 0 times cosine of pi over 2 is still just 0, so I get 0 over pi over 2 minus natural log of pi over 2. We're running out of room here, sorry. Times the sine of pi over 2. Well, the sine of pi over 2 is equal to 1. So this first term, pi over 2 to the power of 0, becomes 1. So I get 1 times negative natural log of pi over 2. So this becomes just negative natural log of pi over 2. That is f prime of pi over 2. All right, we have one more theorem here, and then a very fun example. So if b is greater than 0 and b is not equal to 1, then the derivative of log base b of x is equal to 1 over x times natural log of b for x greater than 0. And similarly, the derivative of log base b of absolute value of x is equal to 1 over x natural log of b for x not equal to 0. So this is a theorem that tells me how to find the derivative of log base b of x. And this will help us a lot, including in the next example. So we want to find the derivative of f of x is equal to x squared plus 1 to the power of 4 times e to the power of x over x squared plus 4. Wow, so without what we've learned today, we already know how to do this technically, right? But this is a pretty ugly function. If we wanted to find this derivative just using the quotient rule, then we would have to use the chain rule, the product rule, and the quotient rule all at once. So that's not fun. So we would have to use the quotient rule, chain rule, and product rule. And that's very sad. I'll draw a frowny face. Tears. So instead of doing that, this is a trick. I'm going to take the natural log of both sides of our equation. And let's see what happens. So I'm going to take the natural log of f of x, taking the natural log of both sides, is equal to the natural log of x squared plus 1 to the power of 4 times e to the x over x squared plus 4. Taking the natural log of both sides of this equation. So if we remember stuff about log rules, here on the right-hand side, I have a log of a lot of things that are multiplied and divided, right? So this right-hand side is equal to the natural log of x squared plus 1 to the power of 4 plus the natural log of e to the x. I can add these two together since I am multiplying expressions on the top. And then since I'm dividing by the next term, I have minus natural log of x squared plus 4. And next I'll bring this 4 as the exponent down in front of the natural log. So I can rewrite this as 4 times natural log of x squared plus 1 plus natural log of e to the x minus natural log of x squared plus 4. And this expression is still equal to the natural log of f of x. Okay, so now that I have this, I am going to differentiate both sides using the chain rule. Using the chain rule. So we just learned here that if I want to take the derivative of log base b of a function, then I can very easily do that. But we learned on the very first page that the, oops, where is it? Here it is. Wait. Oh, sorry. The derivative of, here we go. So the derivative of natural log of u of x is equal to u prime of x over u of x. So in this example, we have a bunch of natural logs. So I simply take the derivative of each of the arguments here, and that's my u. So my derivatives here will be that u prime over u. So if I differentiate both sides, my left-hand side, which is natural log of f of x, that my u here is f of x. So u prime over u will be f prime of x over f of x. Again, because this f of x is my u, so the derivative of the natural log of f of x is f prime of x over f of x is equal to 4 times, I take the derivative of x squared plus 1, that is equal to 2x over x squared plus 1, u prime over u. The derivative of the inside here is just e to the x over e to the x. So I have natural log of e to the x, while my u is e to the x, and so is u prime. Minus the derivative of natural log of x squared plus 4. I take the derivative of x squared plus 4, which is 2x over x squared plus 4. So this is equal to 8x over x squared plus 1, plus simplifying e to the x over e to the x gives me a 1, minus 2x over x squared plus 4. And again, this is equal to f prime of x over f of x. Okay, well, I'm trying to solve for f prime of x. So I'm going to multiply through both sides by f of x to solve for f prime. So I get f prime of x is equal to f of x times 8x over x squared plus 1 plus 1 minus 2x over x squared plus 4. And I know what my f of x was. It was my very original function. So I'll just replace my f of x here with the original function. So f prime of x is equal to my original function, which was x squared plus 1 to the power of 4 times e to the x over x squared plus 4 times 8x over x squared plus 1 minus 2x over x squared plus 4. Whew. So this was a pretty sly trick. But I do think that some of us would prefer this over using the quotient rule, chain rule, and product rule all in one. So just to recap here, I took the natural log of both sides. I employed the natural log rules in order to break up my expression x squared plus 1 to the power 4 times e to the x over x squared plus 4. And then I differentiated on both sides, and I was able to do that relatively easily using the fact that the natural log, the derivative of natural log of u to the u of x is equal to u prime over u. So yeah, this is a fairly tricky example, but I do think that it's nice to know that we have other ways of finding kind of complicated derivatives. All right, that is it for today. Feel free to watch certain examples of this, again, if you are not feeling super comfortable with it. But I will hope to see you in the Zoom sessions, and maybe I'll see you on Friday. Have a wonderful day.